Greetings everyone, and welcome back to my channel. This is the second video of a series where we will explore a variety of concepts and ideas regarding differential calculus, as well as their practical uses in real-life contexts. Today's topic is the process of differentiation, also known as finding the derivative of a function. In my previous video, I have mentioned how there exists a method to finding the instantaneous rate of change of almost any function without simply estimating it. In calculus, that is called differentiation. Differentiation is the process by which one finds the derivative, or gradient function, of an original function. Very well then, but what is a derivative? It is a function used to find the gradient of a tangent, or instantaneous rate of change at any point on another function, regardless of whether it is linear or not. Here I present you a distance time graph. The blue line within it is evidently not straight, meaning it is not a linear function. It's a section of a cubic function, in fact. Next to that cubic function lies a straight red line. You may remember from my last video that the red line is a tangent, as it is barely touching the blue line at point 44, the point of tangency. The gradient of that tangent is equal to the gradient of the function at the point of intersection, 4 in this case. Fundamentally, the gradient of the tangent will therefore be equal to the instantaneous rate of change at point 4. Derivatives are used to find that gradient. If I found the derivative of that cubic function, I could find the gradient and therefore the instantaneous rate of change at point 4. Before I teach you how to find the derivative of a function, it is essential we briefly discuss notation. Say we are given an equation that begins with y equals something. For example, y equals 2x plus 1. That is our original function, and to denote its derivative we write y prime, y with an apostrophe. This notation tells us solely about the dependent variable, that is, the variable on the y-axis we are calculating using the function. Next, assume we have a function f of x equals whatever, such as f of x equals x squared plus 3x. The notation for its derivative is f prime of x, again with an apostrophe, and this tells us the name of the function as well as the independent variable. The independent variable, as you may know, is the variable on the x-axis, the one which changes. At last, there is a final form of notation for all functions. If we have something like y equals, we write dy by dx. This form names both the dependent and independent variables. All are accepted ways of writing, but sometimes schools or other educational institutions might prefer some forms over others. These are two further examples with different independent and dependent variables that are not x or y. Regardless, we mustn't dwell on notation for too long. To find the derivative of a function in the form f of x equals ax to the power of n, we use the so-called power rule. For those types of functions, the derivative will be equal to anx to the power of n minus 1. N may be any whole number, and a any real number. Many types of functions fit this format of ax to the power of n, such as polynomials and any linear functions, amongst other types. These are ones you will often encounter. A notable type of functions for which this does not work, however, are exponentials. Let's look at 5 examples. First, we have a simple quadratic, 4x squared. Using the power rule, we can find its derivative. We simply multiply everything by the exponent, which is 2, and subtract 1 from the exponent. This ultimately leaves us with 8x to the power of 1, which can be simplified to 8x. As we can see, the derivative of a quadratic is a linear function. Next, we have 6x, which is a linear function. The exponent is not present in that function, and when that is the case, it means the exponent is 1. It is not written simply due to the fact that something to the power of 1 does not change. Once again, the power rule is used. The coefficient of the function remains 6, as we are multiplying 1 to it. However, when subtracting 1 from the exponent, which is also 1, we are left with 0. Our derivative is 6x to the power of 0. Up in the top right corner are some useful formulas for exponents. The first one says that ax to the power of 0 equals a, because x to the power of 0 equals 1. Therefore, when writing the final form, we remove x to the power of 0 and leave 6. When a function is equal to just a number with no other variables in that function, it is a horizontal line. We discovered the derivatives of non-horizontal linear functions are simply horizontal lines on the graph. That is logical, as the gradient and rate of change anywhere on a linear function remains identical. Essentially, it does not matter what point we are looking for, the gradient will always be the same. The truth is reflected on horizontal lines. Regardless of what the x value we input is, the y value will always be 6 in this case. Anyways, we continue to the function f of x equals 15. Recall that if we have just a number, it is a horizontal line on the graph. If we once again look at the first formula in the box of the top right corner and turn it around, we discover that a equals ax to the power of 0. Thus, we know that 15 is actually 15x to the power of 0. Differentiating that function yields us 0x to the power of negative 1, but anything multiplied by 0 equals 0. Consequently, our derivative is also 0. This is true for all horizontal lines, that is, functions which are just a number. If we look at a graph of fx equals 15, we find that the y value, irrespective of the x1, is 15. Essentially, there exists no vertical change, no rise. As a result, the gradient of the function is 0 throughout, and that is reflected on the derivative. Horizontal lines display no change. You may move from one point to any other, and the y value will remain identical. At last, we have our final two examples, which are quite similar. For the first one, we must look at the top right corner once again, though this time at the second formula and read it backwards. A over x to the power of n equals ax to the power of minus n. Alright. This suggests that 7 over x in our fourth example is actually 7x to the power of negative 1. We perform the same calculations as earlier with the power rule and arrive at negative 7x to the power of negative 2. You may leave it at such, though some might prefer if you turn it into a fraction again. Notice how the exponent is negative. We transform that to negative 7x to the power of 2. The final example is quite a similar story. We turn the fraction to 2x to the power of negative 2, and we differentiate to arrive at our derivative. Now, the functions we have looked at thus far are very simple. Fortunately, the power rule works equally well for functions that can be considered more complex. These two are good examples. As previously mentioned, we use the same power rule. However, now allow me to introduce you to another rule. It is a little difficult to explain it in words. As such, I will attempt to demonstrate how it works using our first example function. We have our function. Now let us separate each part of it. We thus have negative 3x to the power of 2, 5x, and negative 6. Additionally, let us pretend these are all independent functions and give them appropriate names. H of x will be negative 3x squared, g of x will be 5x, and s of x will be negative 6. We may now redefine our original function f of x as a combination or sum of the three smaller functions. We now obtain something that looks nearly identical to the first half of the second rule, though with another component added. Now we must treat each smaller function like h of x or s of x independently and find their respective derivatives using the power rule. For h of x, h prime of x yields negative 6x, g prime of x equals 5, and s prime of x equals, well, nothing, it's 0. As already mentioned, f of x is a combination of the smaller functions. Peeking once again at the second rule, we find that the derivative of that function, f prime of x, is actually a combination of the derivatives of those same smaller functions. Hence why we apply that same logic here with our example, and we obtain the derivative of our function, negative 6x plus 5. The fundamental technique is to treat each component of the function separately and find their derivative. Afterwards, you may repeat that with other components as well. Let us quickly repeat this process with our second example. We divide the formula into smaller components, h of x and g of x. We differentiate these two smaller components independently. We add their derivatives to obtain the derivative of the entire function, and the final result is 9 over x to the power of 4 minus 4. In the very beginning of the video, I have mentioned how these derivatives we have continuously talked about are used to find the instantaneous rate of change at any point on a function. Yet we haven't done any of that. Nevertheless, this is the easiest aspect of them, how to use them. Here I present you with a segment of a displacement time graph of a moving car. The function of this graph is d of t equals t cubed minus 4t squared plus 12. And I want to find the exact velocity of the car at 4 minutes. How do we do that? Well, exact speed at 4 minutes would be the instantaneous rate of change, or the gradient, at t equals 4. The derivative of this particular function will provide the answer. We find it using the method outlined earlier in the video, which offers us 3t squared minus 8t. As we want to find a gradient at t equals 4, we take the derivative function and substitute t with 4. Effectively, we're trying to find d prime of 4. Calculating that yields 16. The gradient, and by extension, the instantaneous rate of change at t equals 4 is 16. We can repeat this with t equals 2. Once again, we use the derivative substituting 2 for t and obtain a gradient of negative 4. Now, the gradient may tell us a lot about the function. If it is positive, if our derivative yields a value greater than 0, the function is moving upwards, and the y value is increasing. If it is neutral, or if our derivative equals a 0, the function does not change. Finally, if it is negative, or if our derivative yields a value smaller than 0, the function is moving downwards and the y value is decreasing. Allow me to show you a new graph with the same blue line as well as its derivative in orange. First, I would like you to focus on the orange line, the derivative function, d prime of t. The 2 points on the line that intersect with the horizontal x-axis, or the roots of this function, are the points where the gradient equals 0, and the original function does not increase nor decrease. Looking closely on the graph shows how the 2 roots are located at the exact x-coordinates where the blue line turns. Next, the space between the roots is entirely below the x-axis. Consequently, the gradient is negative and the function is decreasing. Again, looking above at the blue line shows how it is moving downwards. Lastly, the parts outside the roots of the orange line are both above the x-axis, meaning the gradients are positive and the original function, that is the blue line, is increasing in value. Fundamentally, all parts of the derivative function below the x-axis are decreasing, the ones on it are unchanging, and the ones above it are increasing. In our case, at points t equals 0 and t equals 2.667, the roots of our derivative function d of t are not changing. Between t equals 0 and t equals 2.667, d of t is decreasing, and everywhere else d of t is increasing. The explanation section of this video has come to an end, and it is now time to delve into some exercises. The first one is really quite simple, finding the derivatives of these 3 functions. Please, I encourage you to stop this video and do them by yourself first. I will briefly explain how to solve each of them soon. Very well, it is time to look at the first one. First, we separate the two components of this function and find the derivatives using the power rule. Afterwards, we join the two derivatives together to obtain the final one, which is equal to negative 15. We repeat that process in the second one, though this time there are twice as many components of which we must find the derivatives. Following that, we combine them to acquire the final derivative. U prime of x equals 16x cubed minus 9x squared plus 4x minus 1. At last, we must find the derivatives of the independent components, and our final answer is v prime of x equals 24x squared plus 15 over x to the power of 4 minus 6 over x squared. The second and final exercise is slightly difficult and involves something we haven't directly looked at. However, it is undoubtedly possible to solve it with all we have learned thus far. First, we have this function f of x. And the question is when this function does not change, when it increases, and when it decreases respectively. Yet again, I request you do this by yourself first, and once you are finished or give up, you may watch the video. To begin, we must recall how to determine whether a function is increasing, unchanged, or decreasing. Here we have it to remind ourselves. At first, we want to find at what x value the function does not change. Reading through our notes, we find that it is when f prime of x equals 0. Therefore, we must first find the derivative using the power rule. Admittedly, we do not know at what point on the graph it will not change, but as previously stated, we do know that f prime of x will equal 0. We can simply work backwards. 0 equals negative 4x plus 2, and we solve for x. That offers us an answer of x equals 1 over 2. Next, we can select a value for x that is smaller than 1 over 2. I will choose 0, as doing calculation with 0 is always quite easy. We now take the derivative f prime of x and substitute 0 for x. Soon after, we do our calculations to find what f prime of 0 equals. Ultimately, we obtain 2, which is greater than 0. Thus, the gradient is positive and the function is increasing. Given the fact that there are no other turning points on the line where f prime of x equals 0, it means that all values smaller than 1 over 2 yield gradients that are positive. We know that the turning point at x equals 1 over 2 is the only one on the entire line for two reasons. First, it is a parabola, and those only have one turning point. 2, we would have gotten more possible values for x where f prime of x equals 0. Anyways, if all values smaller than 1 over 2 yield positive gradient, it means all values greater than 1 over 2 yield negative ones. The parabola turns from increasing to decreasing essentially. That is true because these turning points always signify points where the function has turned from increasing to decreasing, or vice versa. This fact is even illustrated on the graph of the function. 0.5 or 1 over 2 is the vertex, and everything before that has been increasing. Now we may write our final answers down. The function is not changing at x equals 0.5 or 1 over 2. The function increases for any value where x is smaller than 1 over 2. And the function decreases for any value where x is greater than 1 over 2. It appears we have finished the lesson and the exercises. I certainly hope my video has helped you understand differentiation, which is possibly the most fundamental aspect of differential calculus. Thank you very much for watching. If you enjoyed, leave a like and comment, and give me some feedback on the quality of my video and my teaching. Furthermore, if you have any further questions, you may ask them in the comment section. Have a wonderful day and farewell.